Okay, let's think about how to get the energies for the particle that is not forced to live in the well, but it can tunnel out. So here is the potential. So let's say this is 0. So this is v of x, and this is x. This is 0, let's say minus L over 2 and L over 2. And here we have V naught. V naught, and this is 0 potential, and we are considering energies that satisfy this condition. Right? So these are bound states. So we're going to try to derive the constraints on the energy. The energies will be quantized, they will be discrete, but they will be more difficult to obtain. Remember that when we had the infinite potential, right, say between 0 and L, and the potential was infinite, right, outside of those regions, then we had the wave function was proportional to the sine of kx because of this boundary condition here. And so we obtained sine of kl has to equal 0 as well, and so kl is equal to n pi. That immediately gave us the boundary conditions. So from the boundary condition, we were able to get k. So in other words, k is a function of n. It's discrete, and the energy goes like h bar k squared over 2m. We get the energies. They're also discrete. So it's fairly straightforward to get the energies in that case where we perfectly confine the particle. But now we are allowing the particle to leak out, and it's going to be much more difficult. So our solutions, given the symmetry of the potential, are similar to the solutions for the infinite potential case. But we have explicit symmetry here with respect to 0. So we know that our functions are even and odd parity eigenfunctions. It will look like cosine and then sine and cosine and sine. So in this region, in the middle here, between, let's say, x greater than or equal to minus L over 2 and less than or equal to L over 2, if we're thinking of the even functions, these are the ones, right? The ground state will look something like that. These are the ones that look like cosine of kx, where k is equal to 2me over h bar squared, square root. And for x less than minus L over 2, we have a function that has to it's either exponential growth or decay, but we're going to choose exponential decay. So it's e to the alpha x, where alpha is 2m. We have the potential is not 0 as it is in here, but it's v naught. So we have v naught minus c over h bar squared square root. And the fact that x is negative here ensures the exponential decay. So, so we have a coefficient here, b, we have a coefficient here. And for this region, then, right, given the symmetry, we have to have something like a e to the, minus alpha x, because x is positive and we want exponential decay. So these are the forms of the functions, and we want continuity. So we want, it's completely symmetric. So let's apply the conditions at, say, minus L over 2. So at x equals minus L over 2, right, we have that the continuity of the wave function implies that a e to the minus alpha L over 2 is equal to b cosine of minus KL over 2, but that's the same thing as KL over 2 because of the evenness of the function. And then also the first derivatives, we want them to be continuous. And so what does that look like? Well, the derivative of this this function is alpha a e to the alpha x, and x is minus L over 2, so we get minus L over 2 here, and that has to equal to the first derivative of the function inside evaluated at that location. So the derivative of that is minus bk sine of k times negative L over 2. So let's bring the minus sign out and cancel this one. So those are those are the two conditions that we get from the boundary conditions, and there's no need to look at it here. We'll get the same thing because of the symmetry. And so the energies are in here, alpha and k. So let's try to figure out how to determine alpha and k. So if I divide this equation by this one, I'll get rid of these a and b coefficients, and I'll have only alpha and k, which have the energies in it. So the unknown energies are in there. So we'll do this divided by that. I'll just have alpha, and then here I'll have this divided by that. That's the tangent of KL over 2. There's a k here, so it's really k here. So it's alpha over k. We'll bring those two things on that side, and this is where we get, there's an implicit statement there about the values of the energy, and it's not as straightforward as this, where we can immediately get the discrete set of energies. They're implied here. We'll have to think about this in a little more detail. But this is only half of the solutions, right? We also have the odd functions, and so we're getting half of the energies from this. We're going to have to look at the odd functions and do the exact same thing.